thank you for introduction, and I'd like to thank all the organizers of this ICRA online meeting, and it's very honor, honor for me. And today I will talk about ICRA subcategories, and which is a subcategory of module categories, and give and then give relation between tutoring theory and torsion classes. And this talk is based on my joint work with Arashi Sakai, a master's student in Nagoya University. And this is the overview of today's talk. In the first section, I introduce ICE or ICE closed subcategories of module categories and study ICE closed subcategories by using torsion classes. On the second section, I will establish a bijection between ICE closed subcategories and wide tutoring modules. This is a generalization of support tutoring modules, and this bijection generalizes Adachi-lyama-Reiten's bijection. And the final section, I will briefly explain more thing about Hereditary and Nakayama cases. So now let's start the first section. And maybe most of you know what torsion classes and wide subcategories are. And this is, we just recall the definition and setting. Throughout this talk, lambda is a finite dimensional algebra over field K, and mod lambda is the category of finitely generated right lambda modules. And a subcategory of mod T of mod lambda is a torsion class if it is closed under taking extensions and quotients. And we denote by tos lambda, and this is the poset of torsion classes in mod lambda. So the poset structure is usual inclusion relation. And there is another class of subcategory, and which is wide subcategory. Subcategory W of mod lambda is wide subcategory if it is extension closed exact abelian subcategory of this abelian category, or equivalently, if W is wide if it's closed under extensions and taking kernels and co-kernels. Maybe this is a standard definition. And the ICE closed subcategory is generalization of, contains a class of torsion class and all wide subcategories. So this is the definition. A subcategory C of mod lambda is ICE closed, ICE closed, if it's closed under taking images, co-kernels, and extensions. And so, I call it ICE closed or just ICE closed or ICE or ICEs. And the precise meaning of this is that C is extension closed in the usual sense. And for every map between objects in C, then its usual image and usual co-kernel of lambda modules also belong to C. So it's closed under taking images and co-kernels of maps between C. And from the definition, it's easy to check that every torsion class and wide subcategory is ICE closed. And for example, this A2 quiver case, so there are many, not so many, but there are torsion classes like this. This is a torsion class, and this is wide subcategory, which is not torsion class. And every torsion class and wide subcategory is ICE in general. And let's look at another example. And consider the path algebra of this A3 quiver. Then the Alexander-Reiten quiver is this. And in this case, there are ICE cross subcategory, which is not torsion class and not wide subcategory. Consider this subcategory. Then it's not closed under quotient, so it's not torsion class, and It's not closed under kernels because the kernel of this map is this, so it's not wide. But we can check that this subcategory is ICE closed. It's still closed under images and co-kernels. And this is the new class which I introduced. And maybe this is the reason why I started to considering about ICE closed subcategories. An ICE closed subcategory is a new class of extension closed subcategory of module category, which is large enough but not so large. So in the representation theory of algebra, so there are many research on extension closed subcategory of module category, but in general there are lots of extension closed subcategories, and the ICE closed subcategory is large enough because it contains all torsion class and all wide subcategories, but not so large. The meaning of this will be, I will explain later, but in today's talk, I will show that ICE closed subcategory is controlled by torsion class and tau-tuting theory. And actually, I had obtained a classification result of ICE closed subcategory for particular class of algebras. So hereditary algebras of finite representation type and Nakayama algebra type. And the motivation of my study is to generalize these these results to obtain a general framework for studying ICE closed subcategories. And the absolute aim is to compute all ICE closed subcategories for a given algebra and compute in some sense. And to do this, to study ICE closed subcategory, it turns out that the heart of intervals of torsion classes is very useful. And maybe that this terminology is not famous, but maybe you have seen this construction. And interval of torsion classes is just, so let U and T be two torsion classes, which is such that U is contained in T. Then interval is a subposet of the poset of torsion classes. So it's just usual interval subposet. And to such interval in tos lambda, we can define a subcategory which I call heart. This is the intersection of T and U perp. And U perp is a torsion-free class corresponding to this smaller torsion class U. And this is the subcategory of mod lambda. Maybe some of you have seen this construction, and actually there are some papers which this construction is used. For example, Hasse's reduction on tau-tuting modules and Nakayama-Reiten Thomas, and recent paper by Hasse Pfeiffer on wide intervals, and Tatter's recent paper by on quasi-abelian categories. And the naming heart is due to Tatter's paper, and he actually called hearts of twin torsion pairs. And this coincides with our hearts of torsion, hearts of intervals. The intuition of this subcategory is that this measures a difference T minus U. So for example, if we take a heart from the heart of this interval 0T, then we obtain T. So this is something like T minus 0 is equal to T. And if we consider the largest one and torsion class, then we obtain torsion-free class corresponding to this T. So this can be represented as for this, like this. And of course, T minus T is equal to 0. And we have another this kind of equality, which means that T is an extension of U and heart. This star product is an extension or extension subcategory of two subcategories. So now we will see the example of heart in the next slide. So this is the also underwriting, consider the A2 quiver case, and this is also underwriting quiver, and this is the Hasse graph, Hasse quiver of torsion class. And this is the smallest zero, and this is the largest mod lambda. And so if we consider an interval like this from 0 to some other torsion class, then we obtain the torsion class this. The heart of this is this, and the heart of this is this. And similarly, if we consider an interval like this, then we obtain the torsion-free class corresponding to this. And so maybe in this case, we get this. This is the heart of this interval. And for example, if we consider this, then the heart of this is this. This is a wide subcategory, but not torsion class. So this is just an example. But so maybe you wonder why I'm started to talking about heart. It's because every ICE closed subcategory is a heart of some interval. So this is the starting point of our joint work. So let's say be an ICE closed subcategory of mod lambda. Then there exists some interval of torsion classes satisfying that C is equal to the heart of this interval. So now any ICE cross subcategory can be realized as heart of some interval. And actually there is an explicit construction of this U and T, but you don't have to remember since this is not used later. So to study ICE cross subcategories, so we have to maybe it's the heart of intervals. The studying heart of interval is very helpful. And the naive question is that this. So which interval is an ICE interval? And ICE interval means that its heart is ICE. So since every ICE is the heart of some interval, if we can answer this question, then ICE closed, we can obtain all ICE closed subcategory as heart of such interval. So I will give a characterization of ICE interval in the next slide. And this is the characterization of ICE interval. The following are equivalent for an interval ut in tos lambda. The first condition is that this is an ICE interval, which means that the heart is ICE closed subcategory. The second condition is that there exists another torsion class T prime, which contains T, and this UT prime is wide interval. And wide interval means that the heart of this is wide subcategory. So the situation looks like this. So we have the smaller torsion class U and larger torsion class T, and I'm considering this heart. This is the heart UT. And the second condition says that there exists another torsion class T prime above T, such that this interval is wide interval. It means that UT prime is wide subcategory. And moreover, in this situation, this subcategory HUT prime, HUT is actually a torsion class in an abelian category HUT prime. So since HUT prime is wide subcategory, it's abelian category. So we can speak of torsion class in HUT prime. And this is, so in this situation, this subcategory is a torsion class of this abelian category. And it looks like it's the similar that if we have this interval from 0 to t, then we obtain torsion class t. So it's a similar thing happen. And by using this characterization and the fact that every ICE cross subcategory is a heart of some interval, we obtain the following corollary. So let's C be a subcategory of mod lambda, then the following are equivalent. The first condition is that C is an ICE cross subcategory of mod lambda. The second condition is that there exists some wide subcategory W of mod lambda such that C is a torsion class in this wide subcategory or abelian category W. So this is a little interesting because it's easy to see that every torsion class in some wide subcategory is ICE closed. It's very easy to check. But the implication this is a little surprising because every ICE closed subcategory can be realized as torsion class of some wide subcategory. So this says that the study of ICE closed subcategories is in principle reduced to the study of wide subcategories and torsion class in it. So by using this, in the next section, I will talk about targeting theory to use give some classification of ICE closed subcategory. And actually, if we are given the Hasse quiver of torsion classes, there is a very combinatorial way to obtain all ICE closed subcategory. So this is the Hasse quiver of torsion classes. Then every ICE closed subcategory is obtained as follows. So first, choose some torsion class U. So first consider this torsion class U. Then define U plus as the join of all arrows which ending at U. So in this case, there are two arrows ending at U. So by taking the join of these two, we obtain this. So this is U plus. Then for each torsion class between U and U plus, its heart. This heart is ICE closed subcategory. So in this case, so this is ICE closed, this is ICE closed, this is ICE closed, and this is ICE closed. So and every ICE closed subcategory is obtained as the hearts of such intervals. And but the description of this kind of description is not so explicit, but I can give an expression using the filtration closure of some bricks. So the heart of this UT is the filtration closure of brick labels in UT. So I won't define what brick labels are, but this is due to Nakayama writing Thomas, and the Hasse quiver of torsion classes has the natural labeling, arrow labeling by bricks. So in this Nakayama algebra case, we have this kind of brick labeling picture, and this says that in the previous example, we see that this is ICE interval. Then the heart of this is the filtration closure of the brick labeling between U and T. So we have this label and this label. So we have this description. So at least for targeting finite case, so this gives a way to describe all ICE closed subcategories in this form, filtration closure of bricks. And I will give another way to describe this hat by using tilting theory in the next second section. So let's move to the second section. And second section, I use the Adachi-lyama-Reiten's bijection on torsion classes. So maybe most of you know this result, but Adachi-lyama-Reiten showed that there exists a bijection between functorially finite torsion class, and this is a set of functorially finite torsion class, and support tilting modules. This is a set of support tilting lambda modules. And maps is given by P, and P is defined by the direct sum of X projectives of torsion classes. And the inverse operation is taking the factor module, FSC operator. So, and recall from the previous that every ICE closed subcategory is a torsion class in some wide subcategory W. So, we can use Adachi-lyama-Reiten's bijection to study ICE closed subcategory if the following two conditions are satisfied. First condition is that this wide subcategory is equivalent to some module category mod gamma for some another finite dimensional algebra gamma. And this condition is known to be equivalent to that W is functorially finite wide subcategory of mod lambda. And the second condition is that since Adachi-lyama-Reiten's bijection deals with functorially finite torsion class, we impose that C is a functorially finite torsion class in W, not just torsion class. And this is the restriction on ICE closed subcategory, and I call such ICE closed subcategory W functorially finite. And this is just the same same as the previous slide. So ICE closed subcategory C is doubly functorially finite if there is some wide subcategory W of mod lambda such that W is functorially finite. And this is equivalent to that W is equivalent to some module category. And the second condition is that C is a functorially finite torsion class in W, functorially finite in W. So we have this two functorially finiteness conditions, so we say it's doubly functorially finite. And we denote by DFIs the set of doubly functorially finite ICE closed subcategories. And it actually contains F tos lambda functorially finite torsion class, because if W is mod lambda, then W is functorially finite, and this condition is precisely that C is a functorially finite torsion class in mod lambda. So we have this inclusion. And if we are only interested in tau-tilting finite case, then every ICE closed subcategory is doubly functorially finite. So in the tau-tilting finite case, we don't have to care about this condition. And this is the category side, so ICE closed subcategory side. But in the next slide, I will give a module side, which generalizes support tau-tilting modules. This is the definition. Lambda module M is wide tau-tilting if there is some functorially finite wide subcategory W of mod lambda such that M is tau W tilting. So this tau is different from the Adachi-lyama-Reiten translation in mod lambda, but Adachi-lyama-Reiten translation in this abelian subcategory W. And the precise meaning is that since W is functorially finite, W is equivalent to some module category, and M is wide tau tilting, tau W tilting if the corresponding gamma module is tau tilting gamma module. This is the precise meaning of tau W tilting. And actually, so support tau tilting is support tau tilting is tau tilting modules over idempotent truncation algebra. And considering idempotent truncation is equivalent to considering cell subcategory. And cell subcategory is a special wide subcategory. And so support tau tilting is precisely wide tau tilting modules such that the W is a cell subcategory. So we denote W tau tilt lambda the set of wide tau tilting lambda modules. And so if we define these concepts, then it's easy to establish this bijection. So we have a bijection between doubly functorially finite ICE closed subcategory and wide tau tilting lambda modules. And the maps, this map P is the same. So it's the direct sum, take the direct sum of X projectives of ICE closed subcategories. But since ICE closed subcategory is not closed under factor modules, we don't have to, we can't use FAC, but instead we take co-kernels since ICE closed subcategory is closed under co-kernels. So it's natural. And coc-M is the category of co-kernels of all maps in AdM. And this diagram commutes, which means that this bijection is a generalization of Adachi-lyama-Reiten's bijection. And so in the next slide, I will see example of wide tau tilting modules and this bijection. So consider this A3 quiver case. Then this red one is wide subcategory. And so wide tau tilting modules is tau tilting modules in this wide subcategory. And actually, this wide subcategory is equivalent to the usual A2 quiver module category. So wide tau tilting module is, for example, this is wide tau tilting modules because it corresponds to projective modules, all projective modules. And this is wide tau tilting, and by taking co-kernels, and we obtain, we have to add this, and this, since this, the last one is a co-kernel of this map. And so, actually, there is another example. So, for example, if this is also wide tau tilting because it's this, and by taking co-kernels, we obtain an ICE closed subcategory this. And this is maybe the first example of ICE closed subcategory, which is not torsion class and not wide subcategory. And this is the next example. So this is the Nakayama algebra with radical square 0. And consider the subcategory, the wide, this modules. So this 2, 1 plus 3. And this is actually wide tau tilting modules because it is a progenerator of this wide subcategory. This subcategory is wide subcategory. It's equivalent to the module category of direct product of two fields. And this is wide tau tilting. But in this example, you can see that wide tau tilting module is not necessarily tau rigid because the tau of this in the module category is this. So we have this map. So in general, wide tau tilting module is not tau rigid. So we have to replace the ambient module category to some wide subcategory, this. So the rigid property doesn't hold in general. And I will give a way to obtain wide tau-tilting module from support tau-tilting modules. And wide tau-tilting module is not easy to compute from definition because I have to find all wide subcategories and all torsion or tau-tilting module in wide subcategories. But I will show that I will explain that we can obtain all wide tau-tilting modules if at least if lambda is tau-tilting finite and the Hasse quiver of the poset of support tau-tilting modules is given. This is due to this proposition. So let fac u, fac t be an ICE interval to support tau-tilting modules u and t. Then this means that we have t u and we have this and this hat h fac u fac t is ICE closed. Then the corresponding wide tau-tilting module corresponding to this ICE closed subcategory is this. So t over trace u of t, where trace u of t is the sum of all images from all possible maps from u to t. So this is very natural because the hat is something like difference between two torsion class. So we have to consider a difference like t minus u of two modules. And so this can be realized as this. So we mod out all possible maps from u to t, then we obtain this. And this is the corresponding wide tau-tilting modules. And actually, in the first section, I explain how to obtain all ICE intervals. So combining these results, we can calculate all wide tau-tilting modules for tau-tilting finite case in principle. So this is the Hasse quiver of this Nakayama algebra, the Hasse quiver of support tau-tilting module for this Nakayama algebra. This is also under Reiten quiver, and this is the support tau-tilting poset. And consider, for example, maybe if you remember, this u and this t gives ICE interval. And the corresponding ICE closed subcategory is the hat. And from the previous proposition, this is the coq of wide tau-tilting modules. And this wide tau-tilting module is obtained by deleting all images from this map, this module to this module. So we have to delete this one. So we obtain 3, 2, and 3. And this is wide tau-tilting modules. For example, another example, so if we choose this u, and then we have two Hasse arrows, and this is u plus the join of these two, and this is ICE interval. And actually, so the hat is, in this case, this is wide subcategory, but the hat of this is equal to the co-kernel of wide tau-tilting modules. And wide tau-tilting module is obtained by deleting all images from this map from this. So we have to delete this 2 and this 2. Then we obtain wide tau-tilting modules to 1 plus 3. So this is wide tau-tilting modules corresponding to this ICE closed subcategory. So by this method, in principle, for at least for tau-tilting finite case, we can calculate all wide tau-tilting modules and ICE closed subcategory as like this. And Actually, there is another expression in the as we saw in the first section. This is a filtration closure of these bricks and we have this two expression of ice cross subcategory. And finally, so maybe this is the last section. So finally, I will discuss about Hasse quiver of ice cross subcategories. And so let's first recall the property of Hasse quivers of support taututing modules or torsion classes. And we denote by this. This is the number of indecomposable direct summand of M after isomorphism. Then Adachi-lyama-Reiten's paper showed by using the theory of mutation that the poset this is Hasse regular poset. This means that for each vertex M or each support taututing modules, the arrows starting at M and the arrows ending at M, the number of all these kind of arrows is constant for every M, and the number is equal to the number of indecomposable projective modules. So the underlying graph is a Hasse graph. And it's very natural to consider such kind of combinatorial property for wide taututing modules or posets of ice closed subcategories. And the question is that, is there any analogous combinatorial property for wide taututing modules or ice closed subcategories? And unfortunately, we haven't found such combinatorial property for general algebra, but for hereditary case and Nakayama algebra case, we have a similar phenomena for Hasse quiver. And this is the example of Hasse quiver of wide taututing modules. So wide taututing modules, the set of wide taututing modules has the natural poset structure induced by this bijection. So it means that two modules M is less than or equal to M if COK of M, this ice cross subcategory is contained in this ice cross subcategory. This defines the poset structure of wide taututing modules. And following to the two examples of the Hasse quiver of wide taututing lambda modules. And the black vertices are support taututing modules. So this is the poset, the Hasse quiver of support taututing modules. And so in this case, they're complicated, and red ones are new wide taututing modules, which is not support taututing. So in this case, we add this, and in this case, we have to add this. And so by adding this, so this quiver is not Hasse regular because there are 3 arrows, but there are 2 arrows from this. But by adding this, there are 2 arrows starting from this, so this and this. And for example, in this case, by adding this, there are 3 arrows starting from this. And from this, since we add this, there are 2 arrows starting from this. So maybe some of you guessed the combinatorial property. And so let's consider the hereditary case. And hereditary case, there is more explicit description of wide taututing modules and doubly functorially finite ICE. If lambda is hereditary, then wide taututing modules is just rigid modules. And rigid means that the self-extension vanishes. So modules satisfying this X vanish condition. And this is the global condition. It doesn't depend on wide subcategory, so it's a very simple homological characterization of wide tau-tilting modules. And doubly functorially finiteness conditions on ICRA subcategory is equivalent to just functorially finiteness conditions for hereditary case. So by the previous bijection, there is a bijection between rigid modules and functorially finite ICRA subcategories for hereditary case. And this is the what I had already obtained before. So in hereditary case, so everything is very easy because we only have to consider rigid modules and don't have to care about wide subcategories. And by using this simple situation, we can show the following result. Let lambda be a hereditary algebra. Then for each wide tau-tilting modules, or in this case, just rigid modules, there are exactly m arrows, the number of indecomposable summands, starting at m in the Hasse quiver of wide tau-tilting modules. So if we have two direct summands, then exactly 2 arrows starting from this. And actually, so in this case, for each indecomposable direct summand x of m, there is, and we can construct these modules, and there is an Hasse arrow for every indecomposable summand. And actually, this mu x of m is a generalization of left mutation of support tau-tilting modules. So in the situation of support tau-tilting modules, so some direct summand corresponds to left mutation, so we obtain smaller one, and some corresponds to larger one. But in this case, every indecomposable summand corresponds to smaller one. So this is a generalization, the only left mutation occurs. And the construction of this is just exactly the same as the left mutation. So we take the approximation from x to m over x, and then take cokernels. Then the mu x of m is the direct sum of this and m over x. So this is the same formula for left mutation of support tau-tilting modules. And so we can show this such property for hereditary algebra case. And finally, I will talk about Nakayama algebra case. In the Nakayama algebra case, it turns out that exactly the same thing happened. So suppose that lambda is a Nakayama algebra, then for each wide tau-tilting modules, there are exactly m arrows starting at m in the Hasse quiver of wide tau-tilting modules. So, but the same thing happened, but the proof is very different. The proof for hereditary case uses rigid modules, so wide tau-tilting modules. This is projective side, but unfortunately, I haven't found a homological characterization of wide tau-tilting module for Nakayama algebra. But instead of this, this projective X projective object, I used simple object in ICRA subcategory, and I won't define what simple means, but it's simple in the exact category. And I previously showed that ICRA subcategory for Nakayama algebra bijectively corresponds to epibricks, and epibricks is a certain set of bricks such that it's a generalization of semi-brick. Every map is zero or surjection. So I previously showed that ICRA subcategory of a Nakayama algebra are in bijection with such set of bricks. And the proof is based on the combinatorics of bricks of a Nakayama algebra, and a completely different proof from the hereditary case, but the same thing happened, and I think it's interesting phenomenon. And I will stop here, and thank you for listening.